All right, so let's look at this one. Again, it just says find the reactions. This one might take a little more explanation. You can see there's a structure, A, B, C. It looks like a beam. It's really kind of hard to tell how it's connected here. I probably should add, let's assume that A is a pin, and we will. In the book, you might see some stiffeners here, or a little more detailing in there indicating if that were a fixed connection or not. But this is going to be a pin. We've got a pin here at D and a pin here at B. Those look pretty straightforward. And there's this single link between them. So let's talk about this. I want the reactions. The reactions of the system would be what? Well, I think the easiest one to see is, I want to know what's happening here at A. Now, do I want to know what's happening here at B? Probably. Now, is this considered a reaction where it connects at B? Maybe, maybe not. So it looks like this is a system that you're going to have to probably take apart, because if this is a pin, you have how many reactions? 2. And if this is a pin D, you have how many reactions? 2. It looks like at this point, that's 4 unknowns, and you can only write 3 equations. So something's got to come apart. Probably the best place would be here at B. Why? What's special about B in terms of our forces and moments? What's the moment at B? It's a pin. Hint, hint, nudge, nudge, wink, wink. It is 0. That's a great place to take it apart, right? Because when I take it apart, I'll get 3 equations for the 3-body ABC, and I'd get 3 equations for this section DB. And when we do that, think about section DB. If I did pull that apart, what would it look like? Well, it's pinned at both ends. Are there any forces applied to it externally? No. That's something we talked about earlier. What's that called? That's a 2-force member. So it's not 2 unknowns. It's only 1. Because I know the magnitude. I don't know the magnitude, but I definitely know the direction. It's on this line of action from B to D. Okay? So when I draw my free body diagram... Yeah.
How did you know there's no moment at A?
It's a pin. Right? All pins don't have any moment. Right? Same thing at this pin here at A. If I sum moments at A, what should it be? There's no reaction moment there, right? So my free body diagram for this structure would look something like this. I've got my section ABC. At A, I'm going to assume that I have 2 forces that model my pin. And what am I going to do here at B? Well, normally you would say, in general, if this had some load on it, then you'd have to say, well, there's a BY and a BX. But it doesn't have any load on it. So therefore, it's going to have the same direction as the line from B to D. And it will just be, I'll just call it force at B. And because this is 60, does that say 60 degrees? It's really small. I should make these bigger. That says 60 degrees, so this little angle here will be 30 degrees. Which means if I need the X and Y... Whoa, sorry. This thing is having trouble focusing. Let me try that for a bit. If I need the Y or X components, I'll be able to relate those to FB. So there's really only one unknown here, the force in B, and then these 2 reactions. How many unknowns is that total? 3. Now, how am I going to handle this trapezoidal load? I know the area of a trapezoid. That's easy to compute, right? Average the heights times the base. You're ready to roll. Where's the centroid of a trapezoid? That's a little harder to remember. So I think you all probably see the solution to this problem. We want to break it up into a rectangle and a triangle. And I'll just draw it up here to make it easier to see. So what is the equivalent force of the rectangle? Well, the length of the beam is 9 meters, and the height here on the end is 2 kilonewtons per meter. So that's going to be 18 kilonewtons. and it's going to act through the center, half of 9, 4.5. What about the rectangle piece? And I'm going to hatch that one in because I've seen students more than once when they're going to figure out the area of the triangle, they use this total height here. And that's not it, right? You've already used up 2 kilonewtons for the rectangular part, so what is the height of the triangle? 4 minus 2. It's only 2 kilonewtons per meter. And we all know the area of a triangle, 1/2 base, 9 times height, 2. What's that? 9. And it acts through the centroid of a rectangle. And where is that? Yeah, I always remember it as 1/3 from the big end. So now I'm going to bring those down and put them onto my system. So here's the 9 from the triangle. I left my n off up there. And 1/3, the distance from the big N, or 1/3 of 9 is 3 meters, right? And then I've got my 18 kilonewton force. That's the concentrated equivalent of the rectangular portion. And the distance from A to it is 1/2 the distance, or 4.5. So if I go 3, then another 1.5, right? Does that look about right? Anything else? I think that's it. So now, how do we apply our equations of equilibrium? As we've talked before, we're probably going to sum moments somewhere. Where would be a good place to sum moments? You could do it at A, or you could do it at B. Right? Either one would work. If I do it at A, obviously AX and AY pass through A, so they don't create moment. And I'd be able to get an equation in one unknown. If I do it at B, what do I get? Well, the force at B passes through B, and so does AX. I could get AY. But I'm going to follow with the same strategy I had before. And I'm going to sum moments using right-hand rule. I'm going to sum moments at A. Make sure it's equal to 0. So there's my strategy. So let's apply it. So both my concentrated equivalent forces are going to create what kind of moment about A? Positive or negative? Both are going to be negative. So I'll do the first one, which will be 9 kilonewtons times 3 meters. The second one is 18 kilonewtons. That's the force. The distance from A to that centroid is 4.5 meters. What else creates moment about A? Now, so I can take FB. You could project it along its line of axis and try to find that perpendicular distance, but that's tricky. So what I suggest you do is look at it in component form. There's going to be a vertical component, and there's going to be a horizontal component. The horizontal component passes through A. Doesn't create any moment. So all I need is the vertical component. So what's the vertical component? It's the force FB times what? Sine or cosine of 30? Sine. So I'm going to add that effect to my sum of moment equation. So this component, the vertical component, is going to create what kind of moment about A? Positive or negative? Positive. So that'll be plus that vertical component, FB sine 30. And what's the moment arm? What's the distance from B to A? 6 meters. So we should be able to solve for the force at B. It looks like it's going to be positive. I don't know what that's going to be.
72.
Say again?
72.
That sounds too big.
Negative 36.
That sounds better. Maybe you forgot to divide by something. 30 what? 36 even? Anybody else get 36?
Yep.
Yep. 36 kilonewtons. It came out positive, so I did assume the right direction. Now that should make a lot of structural sense to you. With all this load acting down due to gravity, this link better be pushing up to support that. If it has to pull down to keep things in equilibrium, something's not going right. So this makes sense that it would be up, positive. Okay, now what do you guys want to do? Some force is X or some force is Y? You choose.
X.
X. Thank you, Mr. Kirby. So we will go some forces in the X direction and make sure we're in equilibrium. So what do we have in the X direction? We've got AX, and that's positive or negative? Positive. I got no applied loads here, but I do have a component of my FB, right? There it is right there. What would that be? That's going to be FB cosine 30. Is it positive or negative? Positive. So we got FB cosine 30. And of course I can take my value for FB and stick it right in there and solve for AX. What do I get? Should be negative, right? 31.2. Anybody else get that? Yep. I see some head shaking. Does it make sense that this support needs to pull it to the right to keep it from moving? I said to the right, to the left?
Yeah.
I think so. If you were standing there and you had this beam and you were holding that thing at A, are you pushing or are you pulling to keep it in equilibrium? You're pulling. You're pulling back. That makes sense. Okay, we've run out of options now. We have to do some forces in the Y. So we will. And I will assume up is positive. So starting over here, my AY is up. So we'll assume that's positive. I've got all these forces acting down. Oh, I've also got this force acting up. So let me put that one in there. So that'll be plus FB sine 30. Those are my reactions. And then now I get minus 9 kilonewtons, minus 18 kilonewtons. And again, I know FB. Put that right in there. Looks like AY is equal to what? 9. It's 9 positive? I think so, right?
Yes.
Yep. Cool. So what are the reactions? Well, I can easily, if I slide this down to D, so I'm going to draw a free body diagram now of D. So I know that FB is in this direction, right? Equal and opposite. And also I know from geometry this is 30 degrees. If you were asked to do it, you could find the reactions at D, right? You know FB. You could come down here and say, hey, here's dy, here's dx, and you could find those components. That'd be a simple problem here. You'd find the y component of this, which would be FB cosine 30, and that's dx. And you'd find the vertical component of FB sine 30, and that would be dy, if you needed to do that. For me, this is good enough. Once you find this force, we know it's going to translate down. This would be a pretty easy problem. I'm kind of advising you about that because maybe in mastering engineering, it explicitly wants to know these reactions in the x and y direction. So that's how you would translate that. If you haven't already learned, make sure you read the problem carefully. They usually tell you what sign convention they want, and it's not always what you expect. And obviously, pay attention to the units. It can be a little tricky there too. All right. Any other questions?